Okay. So, hello everybody. I guess you can hear me and follow me. Um, so I just need a quick confirmation that everything is okay and you can hear me. Um, so last week we ended up here. Um, yes. Like we we ended up here with a synthesis of this device for dividing numbers with the SRT division, radix 2 SRT division algorithm. Um, we ended up in this point. I hope you remember all our previous discussions about this. So um, here we have these steps of the algorithm where the device investigates these three digits: A of 8, A of 7, A of 6, and according to these values, we are going on one of these three branches, namely this one for if our quotient digit is 1, this one if our quotient digit is -1, and this one if our quotient digit is 0. Right? From all these points, we are ending in something. Okay. No. No. Right. So we're going from here or here or here. We are going in this point. Okay. This point where we test. Um, yeah, let's use this. Okay. We test if count 2 is is 7. So we need this signal, and this signal is titled CNT2 equals 7. So if this signal is 1, this means that count 2 has the value 7. Okay, good. Now, um, we are either on this branch, which means 1, so it is 7, or it is 0. So if it is 0, then we go here and we increment the counter. Oh my god. Okay, let's use this. Okay, and then we are going back here. Okay, want to go over there. Yeah, still don't know draw these damn things. Like this. And, yeah, okay. Like this, okay? So we are incrementing this. For this, we need, see, um, right here we have a mistake, right? So when we add, we do not activate C4 because C4 is already used over here. So it's C6, C6. Oh my God, C6 and C7, C6, C7, and C6 here. Okay, C6. So that's right. So C6 is here, is just here, because we need to validate the loading or either A or Q with what exits from the parallel adder. And C7 then is this guy. Right. So good, good. Then we'll have to use C8 to increment CNT2 with this counter. So we'll use C8 here. Good. And then what we do here, the first thing that we do after finalizing these 7 steps, 8 steps, sorry, it's from 0 to 7. We we are trying to see if we make correction or not. So we are looking at A of eight, right? So to have these values, A of 6, we have them, right? We have them. So we have A of 8 as well. If A of 8 at this point is 1, it means that we need to perform correction. If not, we are going further. So if we are making correction, we correct both the partial remainder and the quotient. Namely, in order to correct the partial remainder, we add m to a, so it's a is a plus m, and at the same time we will increment q prime. such that at the end, when we subtract q prime from q, we will subtract 1 from the quotient, which actually means correcting the quotient. So we increment q prime. Okay. For that, we use a control signal C7, C6, sorry, to perform the addition, and C9 to increment register Q prime. So we already put C6, but C9 is to be put here. Right? To increment, C9 increments register Q prime. All right. And then we are ending up in the same point, which means here. And after that, after performing this correction, then we shift back. So we are looking at a signal which tells us if count 1 is 0. So CNT1 equals 0. This signal is 1 if counter 1 is 0. If counter 1 is 0, then we have no shift to do. Okay? But if it is not 0, then we'll have to do shifts and then again check signal CNT1 equals 0. So who is this guy? Well, if it's 0, then it's something like this. If it's 0, 0, 0, then this gate will signal that, okay, CNT1 equals 0. So when the signal is 1, then the contents of CNT1 is 0. So now, right now, so what we do here is that we shift through register A to the right. So in A of 7 through to 0 enters what it was before in A of 8 to A of 1. This is shifting to the right. And A of 7, just a second. A of 8 will be 0, right? So it's a logical shift. And at the same time, we decrement the counter. CNT1 So I do not want to, bring back to life a dead horse or something like that by speaking about digital logic, but this is a thing related to the digital logic class, right? Because CNT1 has to be one of those counters that are able to count up as well as counting down. So you have to know how to design such a thing. Okay, so this is the shift to the right, so I'll use C10 to do this. Right, so this is C10. So with C10, as I said, we are shifting register A to the right, C10. And as I said, is C1, CNT1 is decremental. Okay, good. Now, then we make the conversion. Oh my God. Well, the conversion is this. Q, in Q, we will have Q minus Q prime. Okay? So to this end, we activate C6 because we want to load what exits from, the outputs of the adder, which means that we are adding something. We also activate C7 because it's actually a subtraction. We add a minus something. And at the same time, I don't have the space here, but at the same time, I'll put it here, activate signal C11. Why? Because C11 tells us that we are no longer doing arithmetic operations or additions between A and M. We are doing additions, well, in this case of subtraction, between Q and Q prime. So C11 acts here, so that it selects Q prime instead of M, is here, such that it selects Q instead of A, and it's here at this demultiplexer because it selects Q as destination and not A. Okay, good. Now, then after this, the only thing that we need to do is to put the result on the outbus. First Q, the quotient, with control signal C12, and then okay, well, I'm going to put A on the outbus. To this end, we use C13, and then we go to the start stop state. Okay, good. So this is how this whole thing is built. So what we need here, okay, we put C10, maybe, yeah. So we need to put Q, we put it. So when we put Q on the outbus, we use C12 here. And when we put the remainder with C13, which is this guy, right? C13 is this control signal, which validates the link between the output of this all these latches from register A to the outputs. Okay, so yeah, this is it. This is the synthesis, not the synthesis, the entire synthesis, because of course you will have to perform more synthesis for this control unit such that you will, generate all these 14 control signals, internal control signals. Okay, so this is it for our uh, discussion about how to implement this um, device. Of course, if you want to design the control unit, you can use all your knowledge from the digital logic and computer architecture classes. So I don't think that I should, put more pressure on you on this side, because you should already know about these things. So let's start a new chapter in our discussion, chapter 2, um, computer performance. First of all, I need to know from you if you can hear me, if you can follow me, right? Everything okay? Um,
David Busitis said
okay,
yes.
okay, good.
David Busitis said we can.
Great. So,
Darius Aprioiu said it's okay.
so um, what we are talking about here is I mean, we are talking about computer performance, but we have to admit that there are basically three types of computers, right? So, first of all, we are talking about, right, desktop computers. These computers are the best known form of computers, obviously, and it's uh, basically what is a desktop computer is basically a computer that is designed to be used by an individual, right? That's why you have a mouse, you have a keyboard, and display and all that, a working station, so to speak. um, so right, it's designed for one user, and everything that derives from, I mean, even the architecture derives from this uh, fundamental thing, that is a system designed to, you know uh, be used by a single person. Now, um, it delivers good performance to single users at low costs, more or less, in these days. I, either I mean, we can talk about laptops or desktop computers. They're basically kind of like the same thing. Um, Nonetheless, the evolution of many computing technologies these days is and was driven back to this day by this class of computers. This class of computers, which is now more than 30 years old. So it is the most know the you know the most famous type of computer. But we are also talking about servers. And these computers, of course, you know that they are designed to be used by many persons, many individuals. Um, they were historically once called mainframes, mini computers, supercomputers. Now we are talking about other, yeah, we are still talking about supercomputers, um, but we are also talking about data centers. Well, supercomputers have this property that, okay, they are built to serve many users, but on the other hand, they can also perform very complicated computational tasks, which are single, right? Single, very complicated computational tasks, such as, I don't know, protein folding, or simulating quantum phenomena, or simulating weather, right? So these are very complicated single um, task, single computational task. They are also built to serve many users. On the other hand, data centers are well designed to serve. I mean, they are mostly designed to serve scenarios in which there are many users, but they perform not very complicated tasks, right? So many users performing not so complicated stuff, such as, I don't know, accessing web pages, or booking flights, or stuff like that. Those are data centers. We are talking about, for both supercomputers and data centers, we are talking about hundreds of thousands of processors. We are talking about terabytes of memory. We are talking about petabytes of storage, right? So, and the cost of such computers is not that affordable. I mean, you cannot, I mean, unless you are some, some tycoon or something, you cannot have such a computer in your backyard. Um, of course, there are more servers and all that, but we are not talking about this here. Okay, so this is this is the second type of computers, and the third type, which is these days is the most common, maybe, if we are to consider the number of processors that are um, actually manufactured these days. Most of the processors manufactured these days are built to be used in embedded computers. And an embedded computer, I guess we already discussed this I guess in our first lecture or something like that. So an embedded computer is a computer that is built as a component of another system. For instance, I don't know. Um, I told you about the coffee machine in the lobby, in our university's lobbies. Well, these are embedded systems, but also all the processors, or the cars. The cars, actually, these modern cars these days are embedded systems because they incorporate computers that control even, the mechanical and chemical processes that are powering your car, but many other things. So in modern cars, we are talking about hundreds of processors which are integrated in the system, in the embedded system. Uh, Also, your smartphone is an embedded system. Why? Because it's basically a phone, a telephone, which also is a computer. But how can you say that is not a full-fledged computer? Basically, because it doesn't have a keyboard. Well, not a full-fledged keyboard, and maybe the the best element to consider here when we make this we discriminate between computers and embedded computers is that you cannot directly program an embedded computer. Namely, you cannot write your Java code or something like that on your smartphone, let alone running it or programming in Java on or Python on your coffee machine or something like that, or in your car. So you cannot develop software on an embedded computer. Um, these are computers and processors that are designed to be cheap. Uh, um, in servers, for instance, we also need um, aside from, I mean, in terms of performance, we want performance for all these types of computers. So, okay, I'll write performance here. It goes without saying for servers, in embedded computers as well. But, you know, for servers, we are also talking about dependability. Dependability actually is a hybrid or mixed um, 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 concept, which consists of several attributes. One of these attributes for dependability, well, we are talking about maintainability, availability, and so on. But mostly we are talking about reliability. You want your server to be reliable, and this is very, very important. Um, for desktop computers, it is important as a quality indicator. I mean, if your laptop or your desktop computer is reliable, that's a very good thing. It means that the product that you are using it has good quality and all that, but it's not vital. For servers, it's vital. And that is for obvious reasons. Um, but for some embedded systems, because embedded systems are by definition um, application oriented, right? So the application drives the design for embedded computers. They are not universal systems. They are built to serve, some type of an application. And depends. It depends. Sometimes for embedded computers, you also want dependability, right? Maybe dependability is not such a vital attribute when we are talking and reliability when we are talking about the coffee machine. Okay, maybe it can be annoying if your coffee is not good or if it does not give change or something like that, but or give some erroneous result, it gives you too much I don't know, sugar in your coffee or something like that. That's not a tragedy. But think about another type of an embedded system, namely, I don't know, an artificial pancreas or a pacemaker, right? Which is made to support the heart beating. This is vital, okay? So you want dependability for this system. So it depends. If your embedded application by itself needs dependability, so the system has to be dependable, right? So these are the three types of computer systems that we want to talk about. And because we ended up with the discussion when we talked about supercomputers and yeah, and we mentioned sizes of, I don't know, hundreds of thousands of processors and terabytes of memory and petabytes of storage and all that. So we need to discuss a little bit about maybe some notation and units of measuring bytes and stuff in our computers. So what is a kilobyte, right? Well, we will write it as 1KB, right? Which is 2 to the power of 10 bytes. Again, 1 byte, 1B means 8 bits, basically. Okay? Um, this is kind of like of the same, it's not equal, but it's of the same order as 10 to the power of 3. So that's kilo in decimal. So that's kilo. Let's get bigger and bigger. So megabyte, of course. If we are talking about 1 mega is 2 to the power of 20, which is approximately this quantity. And then gigabyte. You put this small I if we that's the new notation for if we are talking about bits, right? If we are talking in decimals, then it's 10 to the power of 9. So after giga, of course, there's tera, 2 to the power of 40. Approximately this quantity in decimal. And after tera, there's peta, which we mentioned, right? 2 to the power of 50 bytes. And then we have exa, 2 to the power of 6. And then we have zeta, zettabyte. And 1 zettabyte is 2 to the power of 70 bytes, which in decimal would be 10 to the power of 21. And then we have iota. 1 iota byte is approximately 2 to the power of 80 and 10 to the power of 24. Okay, so that would be, you know, it's hard for the human mind to even fathom, these large quantities. Okay, so that was just a parenthesis, right? Because when we talk about the performance of computer systems, we are, you know, we are measuring a lot. So we need the right measuring sticks, right? So let's talk a little bit about what is performance. Performance is not, maybe not the same thing all the time. And I'll give you an example. I think I have something in one slide, and I have a nice picture for you, and I'm going to show you. It's a table. It's taken from Hennessy and Patterson's book, and it's also a metaphor, but a metaphor that and rather maybe not a metaphor. It's because it's not fake or something. It's not fantasy or something like that. It's real, but it's from another domain. So it's rather an analogy. Um, it's about planes. Okay, and I'm going to copy this and paste it here. Right, so we are talking about this table. Okay, so what is performance? That's the question, right? Like Hamlet's question. What is performance? Um, well, let's see about the criteria. So first, when we are talking about this thing, namely passenger capacity, which is the best one? Well, the best one is maybe the Boeing 747 because it can, it has the biggest capacity, right? But when we are talking about the cruising range, that that means the autonomy of the plane, the best one would be the Douglas DC, which is this guy. So if with a full tank of kerosene, this guy will reach longer distances. Uh, then, but what about speed, right? Speed is a good indicator of performance. Well, the Concorde, which is but is good as an example, Concorde is no longer used because it is considered as unsafe technology. That followed that tragedy in Paris with the accident, Concorde accident. So is the Concorde is the best, but maybe this is not the best indicator of performance. Maybe we have something else as a better indicator of performance, namely how many passenger can I take from point A to point B with a certain speed. I mean, or to put it in other words, how many passenger per time interval will travel with that plane? To that end, you'll have to multiply the number of passengers with the speed. So when you take this into account, the best plane will be, of course, not the Concorde, but um, the Boeing 747, which doesn't have the biggest speed, but it has the bigger passenger capacity and a decent speed, a good speed, and the bigger passenger capacity. So that's why, considering this hybrid indicator, namely passenger throughput, which is another concept. So we are talking about um, speed. Sorry, speed, and here we are talking about throughput. Speed obviously relates to time. Why? Because if you have speed when you're traveling from New York to Paris, then if you have speed, you will have less time to spend from New York to Paris. And throughput is another indicator is the number of people, or in our case, for computers, because we are going to right now to talk about computers. When we are talking about computers, um, the speed, what is speed? Well, when you run a program, a computational task, and you measure the time required to solve it. I mean, to run the program. So That's speed, right? So you are measuring the execution time if you are considering speed as the main indicator of performance, right? So I'm measuring execution time for computers. For computers, we have execution time. But when we consider many, right? So this is the speed applies to all the passengers in the plane. The execution time, when you execute program after program, is the execution time for each program as an individual. But when you run many programs, so you have for your computer systems, you have many computational tasks, you should also consider the throughput. Namely, the number of computational tasks per time interval. Okay? So, good. Let me take an example. Throughput versus response time. So we have a computer system and we make the following changes. To our computer system. A, or 1. We replace the processor with a faster version. Okay? And 2, we add more processors. Identical. Processors for separate tasks. Now the question is, with the improvements 1 and 2, respectively, what is improved in terms of throughput and execution times? In other words, what do we improve with 1? We improve execution time or throughput or both? For 2, do we improve execution time or throughput or both? For the first one, for um, 1, the answer is obvious. If you replace the processor with a faster version, obviously you improve the execution. But you also improve the throughput. Why? Why is that? Well, if you have this processor, right? You have this processor and you have a queue of tasks. Task 1, task 2, task 3. Obviously, P will serve one after another. That's our assumption. Then, okay, task 1, 2, or 3 are executed faster, which means that the execution time for each and every one of them is improved. But on the other hand, if we improve the execution time, then the time required to execute all of these tasks is smaller. So the number of tasks executed per unit of time is also improved. So this shows why execution time is so damn important. Because if you improve execution time, you improve everything as a result. Okay, so that's with one. But what about two? So obviously you improve with two. So what do you have with two? So you have one processor and you have computational tasks. So you have this situation. When you put another processor, then you will have something like this. T1, T3, and so on. You will have here, right? T2, T4, and so on. So obviously you improve the throughput. In this scenario here, you are doubling the throughput. That's obvious. But what about the execution time? Do we also improve the execution time? Well, that is not so obvious on one hand, but on the other hand, it is. It is obvious that you also improve the execution time. Why? Because let's take T3, for example, or T4. What is the execution time of T3? It's not the execution time for T3 and that's it. It is actually the execution time of T1 plus the execution time of T3. Why? Because T3 is will have to wait after the execution of T1. So I want to execute T3 from the very beginning, but I cannot because the processor is occupied with T1. So the actual execution time of T3 is T1 plus T3, right? That's the execution time for T3. And it's the same, goes by the same logic, the case of T4 as well. So, and for the other T's that are to follow. So it is not obvious, but also the execution time. So you see, there's an overlap. These things are there's an interplay between the throughput and the execution time. They are bounded together in this performance. Um, okay, so obviously, if but there is one case in which you add one more processor, but you don't improve any performance. I'll make this scenario here an example. So you have processor one, processor two. You have these two tasks, task one and task two, and you bring another processor. So there's nothing to be improved. Okay, good. Now let's move move on and define the performance. So as we said, we refer mainly when we talk about performance, we are talking about execution time. Okay. So performance of a computer X, the performance of a computer X when running, I don't know, some program is 1 divided by the execution time of that program on, you know, um, computer X. So this means, this means when we say that performance, the performance of computer X is bigger than the performance of computer Y, it means that the execution time X is smaller than the execution time Y. Good. Now, we are often expressing, considerations regarding performance, computer performance, in terms of, computer X is, I don't know, n times faster than computer Y. Well, this means that performance X divided by performance Y is equal with execution time Y divided by execution time X, n is equal with 9, with n, sorry. So to give you an example with numbers, if computer A runs a program in 10 seconds, so on the computer A, we run a program in 10 seconds, and on computer B, we run the same program in 15 seconds, then performance A divided by performance B is equal with execution time B divided by execution time A, which is 15 divided by 10, which is 1.5. So what we say here is that computer A is 1.5 faster, times faster than computer B. Good. Another thing that we have to mention here is that um, this I mean that there's a certain way in which people that are in this field of computer architectures, there's a certain way in which they talk and in which they express these figures and these um, performance indicators. Namely, um, they want to, on one hand, to be very precise, and on the other hand, to be very clear and not to create confusion by using certain terms, although they are correct. Um, so you see here, it's a potential for creating confusion is the fact that as performance increases, the execution time actually decreases. So using decreasing in the same context with increasing, it can create confusion. That's why in this field, people actually they do not say anything about increasing something or decreasing the other thing. No, they are all. So the thing is, avoid increase or decrease, and use improve instead. Obviously, improve means increasing performance, and decreasing on the same improvement means decreasing the execution time. But in order to avoid any confusion, improvement, and all these things are used instead of increasing and decreasing. Now, let's create a new section here. So evaluating performance. When we evaluate performance, that's 1.1. It was a short intro until this 1.1. How do we evaluate performance? Now, there are two aspects to be taken into consideration. So it's 2, 1. So there are two aspects to be taken into consideration. First aspect is regarding what we measure, and to this end, the answer is we measure time. So what we measure? Time. What do we evaluate? Of course, we evaluate computers, but computers running programs. So the thing is, what computer programs? Only, the answer is only real programs. Right? So Patterson and Hennessy tell us that the only consistent and reliable, robust measure of performance is the execution time, right? The execution time of real programs. And they advocate and not that they advocate, they demonstrate that all the proposed alternatives to time as a metric or to real programs as the item to be measured have eventually led to misleading, actually misleading claims. And misleading claims, well, maybe that's not the worst things that can happen. But sometimes using this type of wrong, measurements and measuring the wrong thing led to mistakes in computer design. So the consequences of not doing this, as I said, um, wrong claims. What would be a wrong claim? Well, a new producer claims that his processor is better than another processor. And if you buy it, after buying it, you find out that actually it is not, right? Because the performance was not evaluated on real programs, or maybe the performance was evaluated with some I don't know, some exotic metric or something which is not time. And when you use the computer, you'll find out that that computer that you bought and has fantastic, performance indicators, is actually worse than your previous computer. So so that's a wrong claim, but can also lead to design mistakes. Because why design mistakes? Because you are trying, by your design, you are trying to optimize something that needs not to be optimized, or something like that. It can happen if you are not looking at the right parameters, and you're not testing your product with the right tool, right? You'll design for something else, not for reality anyway. And in real life, computers will run real programs. Okay, good. Now, when we talk about time, let's analyze this. So first, we'll analyze time. So when we are talking about time, we have to say that this execution time is, when we consider it, is of two types. Well, is the system execution time, and CPU execution time, or in short, CPU time. What is the difference? Well, the difference is this. When you run a computer, the CPU will, require CPU time to execute. But this is not it, because you will have to add to the CPU time, you will have to add to also consider, when you talk about the system execution time, you will have to talk about disk access. You'll have to talk also about memory accesses. You'll have to talk about the input output activities. And you'll have to talk about the operating system overhead. All these things are added to the system performance. But nonetheless, the CPU time is a very, very good indicator, because it's obviously correlated with the system execution time. And when you buy a computer, you'll buy it to be performant, right? To be better than in hardware terms. Or many of these things that we listed here, disk accesses, memory accesses, I/O activities, and obviously operating system overhead, um, these are related to the software part, overhead. Um, they're related to the software part. So you want to standardize in one way or another, the way that you are measuring the CPU time, which is actually the best indicator. So what we measure time, but not just any time. We measure the CPU time. The CPU time, because it's a very good indicator from the hardware standpoint of what would be the system execution time. Good. Now, what do we evaluate? So we said that we are talking about time, and then we are talking about the real programs that we will measure. We will measure. Well, these real programs that a computer runs when it functions, these are called workload. So you give a workload to your computer when you use it, right? Your computer has a workload. The workload all the time is actually a mixture of programs. You don't run just one program, even if you want to, because of the operating system, you'll run many programs at the same time. So you'll have a workload anyway. Um, so what would be the way to measure the performance on a computer such that uh, I mean, you can consider this scenario. You have a computer and you run, I don't know, you are a very experienced user and a frequent user of some program. This is a very common scenario. I mean, just think of gamer, right? When this gamer is playing the same game over and over again, and he knows the performance of his game on his computer, and then you give him another computer. Now, this experienced gamer playing the same game on another computer will, I don't know, if the performance is the discrepancy between those two computers is obvious, it would be obvious for him, right? So it would be obvious for that user which computer is the best, or is which one is better actually, which computer is better out of these two. So but these cases are obviously biased because these users are running only those types of programs, only games or only spreadsheets or only, I don't know, text, processes, stuff like that. You want to have an indicator that will consider all or representative mixture of programs into the future. So people will not simply assess the performance of their computers or the computer that they want to buy or on themselves. They rely on third parties, on specialized evaluators, hoping that the methods used by these evaluators will predict performance for the user usage of their new computers. Right? So, who are these evaluators? Well, in industry, we have what they call, well, denote this subsection as 211 benchmarks. These benchmarks are special computer programs, real computer programs, real applications such as compilers and all that, that we use to assess the performance of a computer. As I said, real computer programs. Because over time, I don't know, many years ago, people also try to use kernels, which are small pieces of real applications, or toy programs, which are even smaller pieces of programs, functional pieces, such as, I don't know, quicksort. So you run an algorithm, and you can see the kernel is bigger than just an algorithm. But the toy program can be a an algorithm, a program that, I don't know, implements an algorithm, quicksort or something like that. Others try to use synthetic benchmarks. Well, synthetic benchmarks. These are programs specially written to test computers, but not real programs. These are not programs that try to solve something from this world, right? So over time, people realize that all these approaches are wrong. So these are all discredited today. And it is the same thing with measuring anything other than time for performance. So all these parameters or metrics which do not involve time are discredited today. Um, so the thing with these benchmarks is that, okay, you have a benchmark, but this is not representative, although it's a real program. You cannot, you know, capture with one program all the situation that can happen in a computer system. That's why for testing computers, the evaluators are not just using benchmarks, they are using the so-called benchmark suits. These are collections of real programs. The goal, so one that so one such a benchmark suit is only as good as the constituent individual benchmarks, right? So it is strong if the parts or the individual programs are strong. Nonetheless, the weakness of one benchmark is lessened by the presence of other benchmarks. So if one benchmark is weak in some regard, it is the other benchmark is not weak in that regard, and so on and so forth. So all the angles, so to speak, are covered by the collection of these benchmark programs. But the eventual goal of a benchmark suit is this: it will characterize the relative performance of two computers, right? So what this means in layman terms, it tells you if computer A is better than computer B or vice versa. Um, and the goal is that the benchmark suit will characterize correctly this, this relative performance, even for programs not in the suit. So even for programs not in the suit. Even for those programs, the relative performance of computers A and B should be the same. And obviously, being if we are to talk about reliable, and we are talking about a reliable metric, uh, these relative performance characterization is also transitive, which means that if performance of computer A is bigger than performance of computer B, and performance of computer B is better than performance of computer A, it should, of computer C, sorry. Um, it should follow that performance of A is bigger than performance of C. So you see here, we are talking about something that is robust, a robust measure. Any robust measure is transitive, right? So this is transitivity. This should be the um, performance, the attribute of any performance metric. You see, that's why in sports, one game is not a reliable indicator most of the time. If the value of the team or the player is I don't know, comparable, right? So for instance, take tennis for instance. I mean, there are often situations in which player A beats player B, player B beats player C, but when player A meets player C will beat player A. Although it should follow transitively that player A should beat player C, but it is often it's often not the case. So that type of indicator is not robust. In computers, it should be robust. Okay, it's the same thing for psychologists. With no, they assess human performance in terms of IQ. IQ at best is it's a good indicator. The IQ is a good indicator of how performant are you when taking tests. But life is not about tests, standardized tests. That's why IQ is not a good indicator of success in life. It's rather a good indicator of insuccess in life. That's what it is good for. Because if you have a obviously you have a small IQ, that's an indicator of insuccess. But other than that, if you have what they call a medium IQ or a high IQ, that's not a good indicator of success in life, and even in science and other fields. So that's it's not reliable. Okay, but in computers, in contrast, we are talking about reliability in computers, right? And these measures. So in computers, when we talk about standard um, evaluation of performance, we are not talking about computer IQ. We are talking about spec. Spec is actually a company. It's called Standard Performance Evaluation Corporation, and their activity in this field dates since the 1980s. Okay, so they are very good. It's they have a website www.spec.org. Okay, so these are these guys from Spec. Um, they have benchmarks that cover different application classes, but the most important benchmarks maybe are the benchmark for PCs. So they have specific benchmark for PCs. And for PCs, they have two classes of benchmarks: processor intensive benchmarks and graphical intensive benchmark, or graphics rather. Obviously, we're interested here about processor-intensive benchmarks, and to that end, Spec has created benchmarks. Spec since 1989, so we have Spec and 89, Spec 95. We have 92 rather. So the second was Spec 92, then Spec 95, then Spec 2000, then Spec 2006, and the latest one after a big gap is Spec 2017. But Spec 6 is also used in parallel these days. So we have Spec 2017, but Spec 2006 is still used in some instances. And of course, this is a suite of programs, meaning that we have several programs, a set of programs. For instance, the Spec 2006 consists of a set of 12. It's called Spec int. These are programs in fixed point, and they have 17 Spec floating point programs, right? So 12 fixed point programs and 17 floating point programs. These are programs that are a little bit, they are real, but they are a little bit modified to be portable on any computer and computer system, and such that they are modified also such that they minimize the effect of input-output operations. And of course, these are designed for single processor systems, right? We're talking about single processor systems. However, we also have server benchmarks. Or spec. The idea is this. I mean, the simplest benchmark for servers is a processor throughput oriented spec, such that spec 2006 or spec 2017 benchmarks can be used in order to construct a simple throughput benchmark. How? Well, if you have a system with, I don't know, 100 processors, then you run 100 spec, I don't know, 2006 on your server, right? So you multiply the number of processors with specs, and you run that number of specs on your server, and the result would be a spec, so-called spec rate. Which is actually a measure of throughput. How many specs are run in a given unit of time. Now, regarding the way that we, in this field, we report results, well, the focus here is on reproducibility, so, or reproductibility, such that, because why we are talking about an experiment here, right? It is an experiment actually. You run a test consisting of a bunch of programs, a well-defined collection of programs, and you measure how much time it takes to, execute each and every program. So it's an experiment. So you will have to record the times, and you will have to list everything such that such that another experimenter w- would obtain the same results, will reproduce your result. So if you run your experiment on a computer, you'll have to say what type of computer, what type of other software is running over there, and so on and so forth. What version of software, what version of operating system, everything such that the the results can be reproduced. And then there is this problem of summarizing performance results. Well, here there are things that we must discuss, and we have a little bit more time to discuss it. It's not rocket science or anything. So the thing is that, you know, how can you summarize this? Because you are measuring times, you are measuring how many seconds would it take to, run program one, run program two, and so on and so forth. And I'll give you a picture of spec 2006. I mean the evolution from spec 89 to spec 2006, and see how the collection of programs has evolved. So you run each and every program, and you measure the time required to run that program. So you want to put everything in one number, the performance of a computer in one number, because what you get at the end of the experiment is an array of numbers, right? The time required to run program one, two, three, and you saw for that example for spec 2006 that we are talking about 29 programs, okay? So it's an array of 29 values that you get at the end of the day. So how can you collapse these 29 numbers into one of them? Obviously, the first thing that comes to your mind is to use, you know, um, um, the arithmetic mean, the arithmetic average. But this is not okay because some programs will take longer than others, right? So, for instance, you have, I don't know, some simple program, some compiler maybe, and you cannot compare a compiler with, I don't know, a quantum computer simulator. Both of them are present in spec 2006. The quantum computer simulator will obviously require more time. So that's why you will use not the spec per se, the natural or original spec, but rather a spec ratio. And the spec ratio is the execution time. Spec ratio for computer A. Execution time of a reference machine divided by the execution time of that program on computer A. Okay? Obviously, this means performance of computer A for that program divided by the performance of the reference machine. Right? So we are not talking about absolute times. We are talking about ratios right now. So that's how we eliminate this bias when we measure different times. I mean, programs. We compare programs that run longer with programs that normally will run in shorter amounts of time. And then, how do we collapse these times into? If we are talking about ratios, how do we collapse these 29 ratios that we obtain in one big ratio? Obviously, we need to use an average, but not the arithmetic average, because the arithmetic average is not working well for ratios. So we will use the geometric mean. So if we are talking about um, um, spec ratio for machine A, for all the programs, right? For all the programs in the benchmark suite, then we talk about this ratio of where spec ratio AI means the spec ratio for machine A running program I, right? So, and with this I'll finish, is the same thing as execution time reference I, which means the execution time program I will require when running on the reference machine divided by the execution time required by machine A when running program I. Now, this means that when we are looking at the relative performance of two machines, then we are looking at, right, when we compare spec ratio A with spec ratio to see which one is better. Right? Oh, damn it. We'll have something like this. Okay, and this is equal with, and that's the beauty of the arithmetic mean, that you can collapse it as this execution time reference I divided by execution time AI divided by execution time reference I divided by execution time I. So you see, these are, you can simplify them, which is eventually, right, the geometric average of the performance ratio. What you see here, and the conclusion of this, is that the time and the performance and all those numbers coming from the reference machine are rendered irrelevant. Eventually, if you make this ratio of specs between the spec ratio of machine A divided by spec ratio of machine B, actually it gives you the geometric mean of the performance ratios, individual performance ratios for all programs, from program I being 0 to program I being, I don't know, 28, right? So that's the idea for today, and we end our discussion today. So thank you very much for being patient with me. I wanted to end this part with spec and performance evaluation, and now I will leave the streaming and go on Discord and answer your questions if there are any questions, and also I will provide you the all these captures of hand, hand handouts that I draw here in this. Okay, so see you on Discord for discussions.